You're going to hold me accountable. How many times are you going to listen to that? Sam has 5 problems. There's 4 problems that are worth 100 points, and there's a bonus problem that's worth 30 points. So you can get 130 points out of 100. Okay? You know what is it going to do to your average? It should. And you can calculate, it's not going to go up by 30% if you get 130. It's going to go up by much more because the test is calculated of 100, but you can get 130. You know what I mean? Canvas, I'm not sure if Canvas allows it, so we'll have to use Excel to manually massage it. Okay? Now, this addresses, like, me and TAs get a lot of emails about homework, that you missed the homework. It's not a big deal if you missed the homework. First of all of the homeworks are worth 15%. Okay, so one homework is going to be what, 1% of your grade? And I want all of you to pass. What's the passing grade for this course? No. Like, we grade, actual grade. C? Okay. Now, if there's somebody who never attended any lectures and who haven't submitted any homeworks, and that's the reason they're failing, there's nothing I can do about that. Okay? But if I see you here, which is by the way, is so I heard that Hess he has quizzes in every lecture, and they're worth 90% of the grade. So I may want to try that next time. I mean, I understand it is an effort for you to show up in class. It's an effort for me to show up in class. It's mutual. So just stick around. My intention is to teach you and make sure that you understand major concepts of material science, and maybe have some fun at it. I don't know if you can have fun, but I try to. Okay? So, first question. It has to do with an error function, and we've done a problem like this in the lectures. So you get a table of this error function, and when you do the calculation, and if the actual value is not in the table, what do? Interpolate. I was going to say extrapolate. What's the difference between extrapolate and interpolate? Extra means out, in means in. So you're going to find a value in between. So, all right. We have an alloy which contains a certain composition, and the composition is given to you. And then it undergoes a process at a certain temperature, and you're given the diffusion coefficient and the activation energy for that process. Okay? So these are the 4 inputs you have. Is the composition, temperature, which if you ever do any calculations needs to be converted into Kelvin, right? Then there's a D0 diffusion coefficient and the activation energy. The first question, which is worth 10 points, is asking to find the diffusion coefficient at process temperature, which is given. The second question is worth 10 points, but it's asking, you get 2 more, you get You get 3 more parameters that are involved. You have a certain depth, and you have a concentration. So you have surface concentration, and you have the concentration at a certain depth, and you're asked to find the time that will be required to achieve it. You know why I'm telling you this? All of this? Why am I telling you this? Why am I telling you what's going to be on the exam? That's what you think. That's what you're going to do. From my perspective, it reaches an educational objective. Because once you know what's going to be an exam, you're going to find a similar problem in the book, and you're going to look in the lecture notes, because there's a similar problem in the lecture notes. And what are you going to do? You're going to practice. Okay? That's my intention. And this is not cheating. This is me encouraging you to perform a certain action, which you will. Right? And how many times are you going to tell me after that? How many times you listen to this recording? I want to know. Yeah, make some money. Sell it for $1 to each of the students. Especially so that you can adjust your time. You know what I mean? Like, problem number 2. You have an alloy, and you're given the yield strength, and you're given the elastic modulus. The problem has 3 questions. Each one of them is worth 10 points. The first question is giving you the cross-sectional area in square millimeters. And you're asked to find the maximum load that can be applied to this specimen without plastic deformation. The trick here is that the area is given as in square millimeters. So in SI units, you have to convert that into square meters. And that's, you know, you have to figure out what's the conversion factor. Because millimeters to meters, you divide it by what? 1,000. But a square is 1,000 squared. So that's going to be the difference. This is the trick. So don't make a stupid mistake of conversion. It's not worth it. Okay. The second question gives you original length. And it's asking you to what length it can be stretched without causing plastic deformation. And the third one is about Brinell hardness. You have a certain diameter ball for the Brinell hardness tester, and you're given a diameter of an impression that is made, and you're given the load. And the question is to calculate Brinell hardness in HB. This is a tricky problem because you have to figure out that Brinell hardness thing. Okay? And if I didn't tell you this up front, I don't think it would be really fair to ask, because I don't even remember the conversion. to be honest with you. But I'm telling you up front, so make sure you know how to calculate Brinell hardness if you know the impression, and if you know the diameter of the ball, and if you know the load that was applied. Any questions about the second problem? All right. The third question is worth 20 points. It gives you the true stress, which produces plastic true strain. There's two values you have. The question is, how much will the specimen elongate when the true stress reaches a different value? And you're given the original length of the specimen. And you need to assume a certain value for the strain hardening exponent. That's also given. This is not an easy problem. Yes. I'll try to explain to you what's going on. We're taking a specimen. And we are elongating it. Like this. Except that this is not rubber, but some sort of an alloy. So initially it deforms elastically, so there's a straight line. At a certain point, it starts to undergo plastic deformation. If it was perfectly plastic material, it will give you a plateau. Under constant stress, it will continue to flow. But it strain hardens. So the slope between the stress and the strain in the elastic region is what? Modulus of elasticity. And then in the plastic, the slope is a strain hardening exponent. You're not given the elastic modulus, so you have to figure out what the elastic modulus is first. I mean, to solve this problem, you really need to understand the whole mechanics. So please study for that one. Come to the help session tomorrow. Any questions? Okay. Yes? You didn't get it? No, that's okay. I don't mind. Which chapter was mechanical properties? Do you remember?
What chapter is on this exam?
I knew you were going to ask me, and I'm not prepared to answer because I don't. I'm telling you what the problems are, but it looks like. Well, let me finish, and maybe I will be able to answer. Okay. All right. You see this stress strain curve? Okay. Material initially deforms elastically, and then it starts to undergo plastic deformation. So when you take a paper clip and you bend it 90 degrees and you hold the load and you let go, what happens? It relaxes. You're going to take that paper clip and repeatedly bend it back and forth. It's going to start to strain harden. Strain harden means that you're following this red curve. And the slope of this curve here is the strain hardening exponent, which is given in the problem. So you really need to understand the stress strain curves. You really need to understand the difference between elastic and plastic deformation. Okay? So yes?
For the elastic region, does it still fall into that shear stress strain equation, or does it do that stop?
Well, what do you think right here?
I think we have to separate it into the calculation.
You need to find out what the elastic modulus is because you're given this data point right here. So if you're given this data point, how do you find the elastic modulus? So you can get this part of the curve to reproduce it, and then knowing this exponent, strain hardening exponent, you can plot that. And once you can plot that, you can do the rest of the problem. So essentially, you can reconstruct the whole stress strain curve. How many of you have taken mechanics of solids, mechanics of materials? Okay, that should be very easy for you. And the rest of you are going to study and figure this out and learn something. That's what I'm trying to achieve. And you're going to get partial credit if you don't get it right. Okay. Question number 4 is worth 10 points. It has 2 parts to it. You're given the grain size and you are given the yield strength. And then you're told that if grain size is changed, meaning reduced, then the yield strength is increasing to a different value. This is Hall-Petch relationship. The first question is asking to find the material constant, sigma 0. And the second question is asking to find the grain diameter when the yield strength would be another value.
Can you repeat the B question, please?
Which question?
The B part?
Yeah, so the whole idea of this course is to control the process, to control the structure, to control the properties. We control the structure by changing the grain size. How do we change the grain size? Different ways. One of them is heat treatment. The grain size affects yield strength. This is the Hall-Petch relationship. the yield strength is equal to sigma I, which in this problem is sigma 0 that you're asked to find, plus K times D to minus 1/2. It's just, yeah, like that. Because this is for a thin film. And let me find a better one. Okay, 528. Yes. Hall-Petch relationship, it's in the book. Boy, this is going to be. You're going to learn so much. I'm really amazed. When do we talk about strengthening mechanisms? Yes. Is it chapter 7? Which slide? See, you already know everything. Better than me. Okay, this is the equation. So the first part is asking to find the sigma 0. The second problem is asking to find, gives you the yield strength, and it's asking to find at what diameter of the grain, what size of the grain that's going to happen. It's very simple if you understand, right? It's a simple equation, but you need to know which equation to use. Hall-Petch. You can see that basically based on this equation, if you go into the nano grain size, the strength is going to shoot up, but unfortunately, it doesn't happen this way. So people spend a lot of money and time on research, and eventually this breaks down, but for regular metallurgy, for bulk, it works just fine. Okay. A bonus problem. Wow, it's worth 40 points. Is that right?
Wait, I'm confused.
2 questions, each one is worth 20 points, but I guess the previous is worth, I don't know, maybe I fucked up the math, it's possible, but maybe it's worth, let me do the count. So let's do the count. Let's do it with me. So problem number 1, 10 and 10 is 20, right? 20 plus 30 is 50. 50 plus 20 is 70. 70 plus 10 is 80. And the last one is worth 40, so you can get 120. 120 over 100. But the last one is worth 40. He was late. That's all I can say. The last question has to do with creep. And you've given a table of strain rate at two different temperatures. And you're given the stress level at which this happens. See, you don't even need to do the conversion of the temperature, it's already given in Kelvin. You have the value of the stress exponent N for this alloy. First question is asking to find the activation energy for creep. And the second question is asking to find the steady state creep rate at a higher temperature and a different stress level. Well, it's a bonus problem. 40 points.
Can you say what the first part was asking to find again?
First part was asking to find the activation energy for creep. So once you have the activation energy for creep, you can solve the second part, which is the creep rate at a higher temperature and a lower stress level. So you remember this natural log of exponential equation? Yeah, that's what you need to do. Where did we talk about creep?
So is this exam out of 80 points? Like, if we didn't do the bonus question, that wouldn't lose us any points?
Yes, that's the idea. I need to explain it to the TAs. So you can get even more. Looks like
The bonus won't hurt us.
the bonus is going to help you.
So can you get like more than 100 in the test?
Can you get what?
You can get more than 100 in the test?
Yeah.
Yes.
120. If I did the math right.
Wait, I thought you said it was 130.
Man, this is like quite a bit. And the average in the first test was only 70, so I don't know why am I doing it. But I'm doing it. Okay. You're good now? Yes?
How much marks is question 4 worth?
How much?
Marks is question 4 worth?
You mean points?
Yeah, how much points?
You're from Australia?
I'm from Trinidad.
From where?
Trinidad in the Caribbean.
20 points each question, so 40 points. I mean, the way it happened is I asked the TA to make the test, and they made the test. And then I was thinking, maybe I should give you a bonus problem, like a true false. But then I said, you know what? Time is short for this test, or just about over an hour. So I made this last problem. And here's the problem. This smartasses, those TAs, they think that you know everything. They think that they know everything. Didn't you get a feeling? So to them, it's easy. It's also very easy if you have a solution manual. I can tell you that. But when you're sitting over there, and I know what it feels like to sit over there, you're like, I don't know how old I was when I stopped getting nightmares that I have an exam. But, yes. Yeah, absolutely. Yeah. If it was up to me, I have an open book exam. I don't care. But the reason I cannot allow an open book exam, because how many of you have a physical book on paper?
I'd buy one. If it was open book, I'd buy a book.
You'd buy it for this test?
Absolutely.
For what reason?
It helps.
What stopped, I'm sorry, what?
It would help.
No, wait, somebody said something. There was a female voice. What did you say?